ID, the Future, a podcast about evolution and intelligent design.
Welcome to ID the Future. I'm your host, Andrew McDiarmid. Well, today it's my pleasure to welcome Dr. Eric Hedin to begin a two-part discussion on the finely tuned origin and availability of metals for human use, and how metals play an essential role in the cellular processes that keep us alive. Dr. Hedin is Professor Emeritus of Physics and Astronomy at Ball State University in Indiana. He is author of the recent book, Cancelled Science: What Some Atheists Don't Want You to See. He speaks regularly at universities around the country and writes on the evidence for intelligent design at evolutionnews.org. evolutionnews.org. Dr. Hedin, welcome.
Thank you, Andrew. It's a pleasure to be with you again here and looking forward to our conversation today.
Absolutely. It's always fun to unpack the articles that you're writing at Evolution News. You regularly contribute articles to our flagship news and commentary source, evolutionnews.org. And earlier this year, you wrote a series of 3 articles on metals and life that I wanted to unpack a bit on the podcast. Mm-hmm. In your first article, From Stars to Cells, you write this: "The story of metals and their utilization by humans reveals substantial fine-tuning, involving features of planet Earth that are complementary with human cognitive and physical abilities. The significance of metal usage for humanity is such that eras of human history beyond the Stone Age are commonly demarcated by the prevailing usage of certain types of metals. Copper, bronze, iron, and other metals and alloys have profoundly influenced cultures, artistry, economies, trade, warfare, and inventions, leading to our modern technological society." So, our ability to utilize metals throughout our history seems to be dependent on 2 main things you're pointing out here: the availability or accessibility of metals, and the skill and ingenuity we possess to make metals useful to us. Let's start with the availability of metals. Where did metals on Earth originate?
Well, again, this is actually a very large topic, and I kind of was following up on a recent article that mentioned a type of fine-tuning that had recently been discovered to make the availability of metals for human use more practical. And as I got into researching the topic of metals and reading more, both in books and in articles, it just expanded to become a fascinating treasure trove of information, and much of it really highlighting, again, as you mentioned, the evidence for design. And so back to that question of where did metals on Earth originate? If you kind of want to trace them back to their ultimate origins, astronomers and those studying cosmology will tell us that metals formed within the cores of stars, and it's a part of the process of nuclear fusion by which stars produce their energy, converting lighter or lower atomic weight elements into heavier elements through fusion and releasing energy in the process. And so this process of stellar nuclear synthesis is where all the metals came from. That's actually a long, complicated process that involves the life cycles of multiple generations of stars. In the early history of our universe, stars from their birth throughout their lives, and then their end stages of going supernova and spreading their core materials, including metals, throughout the universe that could then be kind of collected gravitationally into new star systems and planets such as our own. So it is not a simple, straightforward process when you look at it from what we have discovered about nature. There's a lot of ongoing study with this. Some of the more recent evidence from astronomy indicates that certain metals might have also been formed in more exotic conditions out in the cosmos, namely from neutron star mergers, where you have 2 neutron stars that are orbiting each other, and as they merge, there's energy released that could be the energy required to produce heavier metals by fusion, including one that we're all familiar with, the metal gold.
Yeah, it's truly fascinating that it happened so long ago and these metals came to us from so far away. We kind of take that for granted. We find them here on Earth and we think, oh, they've always been here. But no, they come from far away and from very complex processes that involve stars throughout the galaxies.
Yes, far away, both in space and in time. I think that's interesting, and physical processes that are complex and going on far beyond our own planet. In the cores of distant star systems.
Yeah. And just for clarity's sake, so that we're clear on what metals we're talking about, can you list some of the key metals that originated in the stars and were deposited here on Earth? I know I mentioned copper, bronze, and iron. What are some of the others?
Well, it's interesting, actually, that astronomers classify any element heavier than helium, anything with an atomic weight greater than helium, as a metal. And really, in the primordial origin of the universe, we didn't have metals except perhaps very trace amounts of lithium. So all these other metals were formed by this process of stellar nucleosynthesis, and that again took a lot of time. But so any of the elements with an atomic weight less than that of iron could have been formed within the normal nucleosynthesis process in the life cycle of the star. But all the elements that are heavier than iron, including what we would call the valuable metals that we think of as gold, silver, copper, platinum, cobalt, and even some of the radioactive materials like uranium and thorium and so on, all of those formed during the life cycle end stages of a star in the supernova explosions. And that's a very transient event, and yet all of these familiar precious metals came from those events. So pretty much everything that we consider as a metal today formed within a star at some point.
Now, you write about a confluence of conditions required to bring those metals into our world. First, how did meteors and other space debris play a role in this?
That was kind of like adding some frosting to the cake in a sense. The bulk of our planet would have formed in what we call a interstellar nebula, initially just clouds of gas and dust, which would be somewhat primordial, also enriched with these metallic elements from supernova explosions that occurred earlier in the vicinity of the galaxy, where our sun and solar system was about to form. Once gravity coalesced together the materials that became Earth, there was actually a process known as differentiation. It has nothing to do with math or calculus, but it means that the Earth in its early stage was molten, and the heavier materials, including metals, primarily sank to the core, which is why the core of our Earth is mostly iron and nickel, but a lot of these more uncommon metals would have also been buried deep beneath the surface towards the core. And in order to have access to them today, we needed something else. And I think there's some design and foresight that one could point to in seeing that there was a veneer of metallic materials added to the crust of our planet by bombardment from asteroids and meteors as the solar system continued to kind of settle down. And so probably without those, we would not have on the surface of our planet the accessible metals that we are needing today.
Okay. And here's a question. How did all those deposited metal minerals go from soluble and toxic to insoluble and beneficial to advanced life?
Okay, so again, just, why are soluble minerals and metals toxic in many cases? And well, soluble would mean soluble in water. If you've got a lot of soluble metallic minerals in metals, which are usually combined with other substances, other elements to form minerals, if those are dissolved in the water, then they're going to end up in things that use water, like plants or anything that would need to drink the water. And so those are toxic in that form of just the slightest low concentrations. So how could we see a transition from that form, the original form of the metals to more of an insoluble. And it turns out that it was the metabolic activity of bacteria that actually, over eons of time, at least 1 billion years, transformed the soluble minerals into insoluble ones that could be actually used without polluting the water in a sense. And sulfate-reducing bacteria are a primary source of that. This sulfate-reducing bacteria obtain their energy by oxidizing organic compounds while reducing sulfates, metal sulfates, to insoluble sulfides. So they're kind of a bacteria that breathes sulfate rather than oxygen. So this bacteria not only worked to kind of transform the environment so that it wasn't toxic, but it also, in the process, the bacteria, kind of a byproduct of their metabolism, produced concentrated deposits of insoluble metal minerals, which we use today for mining metals and then using them for our technology. And that helped, as some authors have said, propel humanity's leap from the Stone Age into civilization.
Yeah, so it's notable not only that we have these materials, but that they have been properly processed and transformed so that we can better use them. Interesting.
Yes.
Well, many of us may be aware by now that Earth is located in our sun's circumstellar habitable zone, often called the Goldilocks zone, where planets are not too hot and not too cold to support liquid water and complex life. But few may know that there's also a Goldilocks zone that's recently been discovered between Earth's crust and its mantle. Now, you mentioned this in one of your articles. Tell us about the significance of that Goldilocks zone with regard to the availability of metals.
Well, it turns out that in this recent paper, and this was kind of the springboard for my research into this topic, I wanted to follow up on it, and turned out it became a much bigger, field of research than I initially had been intending to jump into. In this particular case, this Goldilocks zone that has been discovered, it's a combination of conditions kind of at the underground, at the boundary layer between the Earth's crust, at the lower edge of the crust, and then the upper edge of the mantle, which lies deeper than the crust. And it turns out that a lot of the metals which are crucial to our technology, including manufacturing, renewable energy technology, and so on, are more available at the upper edge of the mantle, which is still far too deep below the Earth's surface for us to be able to access them. But this Goldilocks zone that scientists have identified shows that at this boundary layer, right at the crust-mantle boundary, that if the temperature is just right, and they cite around 1,000 degrees Celsius, that metals can then be transported to shallower levels near the surface where they could be accessed through mining. And it turns out that our planet has these conditions for this Goldilocks zone to exist. So these are significant metals for technology. They mention copper, cobalt, tellurium, platinum, very highly sought after, again, due to their use in electronics technologies and even in battery storage devices, solar panels, fuel cells. There's a temperature-dependent zone, this Goldilocks zone, right at the base of the Earth's crust, which they say acts like a valve and can allow the metals to pass upward from that deep level to the upper crust region, where they can be accessed, again, by mining. So again, you think of just all the processes. We started off talking about, long before even the Earth formed, the nucleosynthesis process in stars, and then there were the early Earth formation, and then it had to be supplemented by additional bombardment events. Even the large bombardment event that led to the formation of our moon added a lot of metals to planet Earth. But we won't go into that any further right now. But there's this multi-billion-year time scale for all these processes that are required, that had to be in place to furnish the metals needed for life and human flourishing. So I think that wisdom suggests that this is consistent with the idea of design, and it's a bit of I think, an unscientific stretch to just say, oh, what good luck we have had. In my opinion, in my experience, luck is never much of a satisfying scientific explanation for any phenomenon.
Right. Yeah, and as you say, a confluence of conditions. I mean, if it was just one thing that was kind of set up right, you can say, okay, coincidence. Maybe even two or three, but when there's a confluence of conditions, you really that explanation really loses traction, and at that point it becomes less likely than more likely, and you really have to pay attention to that in science. I mean, science isn't always going to slap you with 100% proof of something, but it's going to be indicative the more you look at something, and you really have to be honest with what's more likely, what's less likely.
Yes, I agree. And so, as long as you are willing to, evaluate the evidence and consider in which direction is it pointing, in which worldview outcome is this evidence indicating that the reality lies. And I think some people are open to changing their worldview and others are not. So it becomes then not a matter of evidence, but just a matter of what you're willing to believe. But I think that if we do look at the evidence, it is strongly consistent with evidence of design.
Well, in the second half of our conversation, we'll take a closer look at how humans have utilized metals and what it reveals about the nature of humans and the design and fitness of planet Earth. But before we close today's episode, let's begin discussing the role metals play in life at the cellular level. In your second article, Metals and Life, a Balancing Act, you write that one of the most fundamental aspects of all life is the ability to derive energy from metabolic processes, notably dependent upon fractional amounts of metal atoms integrated within cellular biochemistry. Now, this is fascinating to think about. Not only are we able to tap into these vast deposits of metals in the Earth's crust and utilize them in a myriad of useful ways, our very lives depend on trace amounts of these metals in our own body. Tell us about the crucial role of metals in life's cellular processes.
Okay, I think this is a fascinating topic, and it's tied into what we talked about earlier, how it actually required living organisms. I mentioned these sulfate-reducing bacteria and other kinds of bacteria that kind of processed the original form of metallic elements on Earth into forms that would be both not as toxic and more available for future technological uses. So life was needed to help make metals available and in a form that more advanced life could tolerate. But then it turns out that advanced life relies upon metals to exist in the first place. And not only advanced life, but also the bacterial life that we mentioned earlier. So it's all almost tied together in a circular interdependence. It's hard to know where do you start with this. But you ask, what about energy that living systems need? And it turns out that, well, that's often dependent upon the existence of trace amounts of metals in organic biochemical compounds that are part of living systems. So life is based on energy gained, at the cellular level by an electron transfer process. And this process, chemists will recognize this. I hope it doesn't get too technical for others, but these processes rely on what's known as an oxidation-reduction reaction, which in cellular organisms is mediated by special enzymes. Enzymes are extremely complicated biomolecules, and these enzymes often contain certain what are called transition metal elements in their structures. So, for example, the process of photosynthesis, producing oxygen as a byproduct of photosynthesis, appeared in the Earth's history somewhere between 3.2, 2.5 billion years ago, according to what studies have shown. And these photosynthetic metabolisms rely on a range of transition metals. And they rely on the metals in a very unique way. There needs to be just the right amount of metals and just the right metals embedded within complex, typically you think carbon-based chemistry for biomolecules, but carbon and nitrogen, oxygen, hydrogen, so on are not enough. You also have to have some tiny insignificant fraction of the total count of atoms being a particular type of transition metal.
Right. And just to give listeners an idea of how important even traces of metal minerals are to life, tell us about this example you write about, the hemoglobin molecule. It's, in terms of the overall atom number versus what's in it of iron. Can you give us that relationship?
Well, certainly. So hemoglobin is a molecule most people have some familiarity with, realizing that it carries oxygen throughout our bodies in the bloodstream. It's again a large molecule, about 10,000 atoms overall. But within that 10,000, there are just 4 metallic atoms, iron atoms, that play an exquisitely essential role in the transfer of oxygen in our bloodstream. So 4 iron atoms out of 10,000 overall. And the thing wouldn't work without those 4 metal atoms that have to be in there. And several other types of enzymes that are essential for biochemical processes also require that trace amount of particular metal atoms in order for there to be life. And I find it fascinating that there had to be just those atoms available, and that somehow the design of the biochemistry was such that they could be placed in the mostly carbon-based molecules in just the right way in order to carry out their functions.
Yeah. And it's amazing how such little of those metals is so vital to different cellular processes. Well, as you surveyed the science literature on this topic, you noted researchers giving lip service to Darwinian processes, crediting natural processes with producing such a delicate and finely tuned balance between metals and life. But why is it highly unlikely that we can credit a Darwinian process with the complex biochemistry that's required for this finely tuned relationship? I mean, you've touched on this a little bit, but I just wanted to see if you would draw that out a little bit more. Why is it highly unlikely that we can credit a Darwinian process for this?
Well, I think that when we actually begin to perceive all the complexity of the biochemical processes that are required for living systems, I think it's important for us, whether we're scientists or lay people, non-scientists, to not naively assume that undirected natural forces have any sort of ability to think ahead and realize what's needed in order to kind of assemble the complex biochemical molecular structures that are needed for life. We're just beginning to kind of reverse engineer cellular processes by studying what exists. We have intelligence and we have training in chemistry and the way nature works, and we're just fascinated at how intricate and involved it is. And there's nothing here that we could have thought of and produced kind of on our own without looking at it and seeing how it already exists. And so with our intelligence and really being insufficient to generate living organisms, I think that it is far from a scientific conclusion to suggest that blind forces, essentially the electric force, which is really all that's involved in chemistry, is sufficient to produce these complex functional biochemical structures that are essential for life. So I believe that it's sort of a worldview posturing that's going on when authors will say, well, look at how the microbes adapted to the availability of different elements in the Earth's crust, and as this or that metal element became available, then the microbial life adapted it or chose to kind of put it into its molecular structures and make use of it for these important enzymatic reactions. Again, if you're looking at it from a natural point of view, there is no ingenuity, there's no foresight, there's no planning, there's no education that has that something is relying on. It's just random. And the complexity is too great for randomness, even by trial and error, to arrive at the solutions that we see pervasive in the cellular structures that we've been studying.
Right. Yeah, I like the way you put that, worldview posturing. And of course, on the other hand, you write that the crucial role of metals in enzymatic reactions is consistent with the characteristics of sophisticated engineering systems and designs. What led you to that conclusion as you reviewed the research?
Well, I think that it's probably common knowledge to those who actually are involved in engineering design and in construction of sophisticated engineering technology. I remember the tragic case of one of the space shuttle accidents decades ago that was blamed on an O-ring, a little rubber ring that was part of a seal, and that little rubber ring failed, and it led to the complete destruction and the loss of life of the space shuttle astronauts. So it seems that it's truism that the more complex the system, the almost easier it is to have it go bad if something simple fails. It mentions this in some of the research articles that I was studying, that in all of these enzymes that use metals as part of their functionality within the cell, the removal of the metal component, and remember, that might just be 1 or 2 or 4 atoms out of thousands, the removal of the metal component always causes a failure, a loss of activity. So it's not like these complex biomolecules could have been working and then somehow a metal atom accidentally got in and they found it worked better. So, okay, let's evolutionarily select for that. No, without the metal element, the 1 or 2 or 4 atoms out of thousands being there in the first place, the whole big thing is a waste. It's functionless. And so I think that there's a great similarity between highly designed engineering systems, where each of multiple parts in the whole functional system is indispensable, and what we see in these biological systems, especially the ones that we're looking at today, the ones that incorporate metal atoms into their structure.
Fascinating. Well, we are going to leave it there for now, but we'll come back in a second episode to further explore the delicate relationship here between metals and life, and how humans have harnessed metals throughout our history. It's really interesting just to know about all this, but it's also fascinating to see how the story of metals provides further evidence of fine-tuning and foresight in the design of our planet. Dr. Hedin, thank you for unpacking this with us today.
Thank you. I enjoyed our conversation.
Well, we'll include links to Dr. Hedin's articles on metals and life in this episode's show notes at idthefuture.com. And for more from Dr. Hedin, I encourage you to read his book, Cancelled Science: What Some Atheists Don't Want You to See. It's jam-packed with lots of evidence for intelligent design across the spectrum of the universe. For ID the Future, I am Andrew McDiarmid. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.